All right, let's talk about something we use every single second of every day, but almost never actually think about. Numbers. In this explainer, we're going to crack the code behind them and uncover the hidden systems that run pretty much everything. So, you ready? Let's dive in. Okay, so let's start with what seems like a super simple question. You look at the number 567, and your brain instantly says 567. But why? How does that actually work? It's not magic, you know? It's a system, a secret structure we all learned as kids, but never really took apart. Well, today, we're going to pull back that curtain. And here's the first piece of the puzzle. The number 567 is really just a kind of shorthand. That 7 on the end, it's not just a 7, it's 7 times ones. The 6 in the middle is 6 tenths, and that 5 out front is 5 hundredths. See? Each digit's actual value depends entirely on its position in the line. And if you want to get a little more mathematical about it, we can write it out using powers. 100 is just 10 squared, 10 is 10 to the power of 1, and yeah, even 1 can be written as 10 to the power of 0. Now, this isn't just some neat party trick for one number. This is the engine that drives our entire number system. It's all built on the power of 10. But that's the key thing to realize here. It's a system. And if our system just happens to be built on powers of 10, that leads to a really interesting question. What would happen if we picked a different number? What if the whole thing ran on powers of, say, 2, or 8, or even 16? And that's where we get this idea of a base. The base is just the number of unique digits you use. So our system is base 10 because we use 10 digits, 0 through 9. And why 10? Well, the most popular theory is almost laughably simple, because most of us have 10 fingers. It's not some universal law of the cosmos. It's just a convenient choice we humans made a long time ago. And as you can see here, our base 10 is just one of many options. A good way to think about it is that each base is like a different alphabet for writing numbers. Binary, or base 2, has a tiny alphabet with just 2 letters, 0 and 1. Octal has 8. And then you have hexadecimal, which needs 16 letters. And that creates a funny little problem. I mean, how do you write 16 different digits when we only have symbols for 0 through 9? Simple. You just borrow from another alphabet. In hexadecimal, after you hit 9, you just start using letters. A is 10, B is 11, all the way up to F for 15. It's a super compact way to write really big numbers, which is exactly why you see it all over the place in programming and computing. But let's zoom in a bit, because out of all these different bases, there's one that is absolutely fundamental to our modern world: binary. It is, quite literally, the native language that all of our digital technology speaks. And this is the reason why. A computer doesn't think in numbers like 4 or 7. A computer thinks in switches. Is the switch on or is it off? Is there electrical voltage or is there not? It's a simple 1 or a 0. Every single thing you do on a computer, every photo, every song, every single word, is at its core just an incredibly long, mind-boggling string of ones and zeros. Okay, so we've got our familiar base 10 world that we live in, and the computer's base 2 world. So how do we translate between the two? Well, it's actually a lot easier than you might think. Let's learn how to speak both languages. Going from some other base back into our good old decimal system is the easy part. Why? Because we already know the secret. It's the exact same formula we used for 567. We just swap out the powers of 10 for powers of whatever base we're starting with. Let's try it with this binary number 1110. That little 2 at the bottom tells us it's base 2. So we just take each digit and multiply it by a power of 2, starting from the right with 2 to the power of 0. Add them all up, and you get 14. That's it. 1110 in binary is just the computer's way of saying 14. Now, let's go the other way. How do we translate our numbers into a new base? This uses a really cool and really powerful technique. All you need to know is how to divide. We're just going to keep dividing our number by the new base over and over and pay very close attention to the remainders. Okay, let's convert the number 893 into binary. We're going to base 2, so we just keep dividing by 2. First step, 893 divided by 2 gives us 446, with a remainder of 1. Now, hang on to that 1. It's actually the very last digit of our final binary number. All right, now we take that result, 446, and we do it again. Divide by 2. This time we get 223 with a remainder of 0. Since we're building our new number from right to left, it now ends in 0, 1. And you just keep this chain reaction going. Divide the result, grab the remainder, and repeat over and over again until you can't really divide anymore. We get all the way down to 3 divided by 2, which gives us 1 with a remainder of 1. That final quotient, that 1, is special. That becomes the very first digit of our answer. So you take all those remainders you collected, plus that very last quotient at the end, and you read them from the bottom up. And just like that, we've done it. We've translated 893 from our base 10 language into the computer's native base 2. But here's where things get really, really cool. These other bases aren't just for translating. They are complete, fully functional ways of doing math. And when you see something as basic as addition from this completely new perspective, well, it can kind of blow your mind. The rules for adding in binary are dead simple. 0 plus 0 is 0. 0 plus 1 is 1. But check out that last one. 1 plus 1 equals 10. Now, that is not the number 10. In binary, 10 is how you write 0 and carry the 1 over to the next column. Sound familiar? It's the exact same thing we all learned in grade school. So let's try it out. This looks like a totally normal addition problem, right? But we're going to play by binary rules. We'll go column by column from right to left, just like always. Okay, look at the rightmost column. 1 plus 1 is 0, carry the 1. Next column, 1 plus 0 plus the 1 we carried, that's 2 again, so we write 0, carry another 1. Next one, 0 plus 1 plus our carried 1, that's another 0, carry the 1. Finally on the left, 1 plus 1 plus the 1 we carried is 3, which in binary is written as 11. Put it all together, 1, 1, 0, 0, 0. It looks weird, but it's totally logical. And that kind of leaves us with a big final thought, doesn't it? We take our base 10 system completely for granted. But just a simple shift in perspective to base 2, to those basic on or off switches, was all it took to unlock the entire digital revolution. It just makes you wonder, what other incredible ideas, what other revolutions are waiting for us, hidden just behind the everyday systems we never ever think to question?